Okay, so far we have covered most of the key concepts of the simplex method, and you are basically convinced that if you have a large linear program, you have a way. But there are still several things to complete the introduction. The thing is that what we have solved are those linear programs with an optimal solution. What if we have an unbounded linear program? May we detect that while doing the iterations? We need to make sure that. And if we have an infeasible linear program, how may we deal with that? So those are the two remaining issues to discuss. Let's start with the unbounded linear programs because it's easier. When is a linear program unbounded? We know by concept. That means there is a feasible solution. There is a feasible region, which is unbounded. And at a point, you may find an improving direction where if you move along it, you may go forever. Then one step, one improvement, and you may move forever, so the problem is unbounded. Our simplex method, luckily or fortunately, can actually find this kind of situation easily. If your LP is unbounded, definitely your simplex method will find it. So let's consider the following example. Suppose I have a maximization problem like this. So first, I get the standard form, and then I get the tableau, and then I do an iteration, -1 enters, 1, 4. This guy is the winner, and then we do this pivoting. Okay, so this one is done. We get the second tableau. And then at the second tableau, nothing special, so we enter x2, and then immediately we see x4 should leave, and then we do the pivoting to get the third tableau. Here, you see that x3 has -1 as the reduced cost, so you may want to enter x3. And then when you do the ratio test, whoop, immediately you see both denominators are negative. What does that mean? Here we say the ratio test fails because none of the denominator is a positive value. So no row should be considered. Why is that? Because this particular thing means if we increase x3, that's going to make x1 and x2 both becomes larger instead of smaller. So that means x1 and x2 will never get a chance to hit 0. So if we enter x3, we are improving, okay, because of this number. And there's nowhere to stop. So we have an unbounded improving direction. As long as you run your simplex method and see that there is any column in any iteration satisfying this condition, then you're done. Your LP is unbounded. Graphically, if we plot that particular feasible region, then we can see that we are originally here, 1 iteration, 2 iteration, and then if we still want to move along the edge, because we are maximizing x1, we will keep moving forever and increasing our objective value forever. That's why this problem is unbounded. And also we can see that we are having basic variables as x1 and x2. They are both positive at this moment, and when we increase the values along this line, both will go up, right? x1 goes up, x2 goes up. So that's why these x1 and x2 constraints will never get a chance to be hit. That's why we have no chance to hit the constraints, and that's why we will never get stopped. That's why this problem is unbounded. So let me conclude. Suppose that we have a minimization linear program. Then as long as we have any column in any tableau having these numbers so that the reduced cost C bar J is positive and all these entering column coefficients are non-positive, then we may stop and conclude that this LP is unbounded. Your positive reduced cost tells you that for this minimization problem, once you enter this variable, increase that by 1, you are going to get improvement. Your objective value will decrease, and that means this is an improving direction. And all your denominators are not positive. That means when you enter xj, either a basic variable goes up or it is not affected by your xj. Then there is no way for them to become 0, and this is an unbounded direction. So you may want to take a moment to think about what should be the unbounded condition for a maximization problem. Okay? You do have some conditions about the size of your numbers here. What is that? What is that condition for the maximization problem? Oh, please think about it.